Alrighty, so let's get right into it. So I'll try to simplify the mole, and I really would like your feedback here. What is the mole really? What do you understand by the term the mole? This is the most probably the most feared topic in chemistry. When you do when you do a survey, when you check out persons who've done it years ago or who didn't like chemistry or whatever, this is what they say, boys, the thing that gave them a hard time. What do you understand by the mole? Anyone? Just give me you can put it in the chat, you can open your mic, you can share. It's meant to be interactive. Holy Childhood Queens, Mobile High, Green Island High, yeah, St. Andrew High School for Girls, Renee Lorraine. What do you understand by the term the mole? And I promise we're not going to spend long on the theory, we're just going to get into the practice. A mole contains the same number of atoms as 12 grams of carbon-12. All right, how many atoms are we talking about there? That's like a definition by comparison. How many atoms are in 12 grams of carbon-12? So very good, Candice Campbell. How many atoms are in 12 grams of carbon-12? Oh, there's a clue. There's something on screen. I think there's a, not a thing. There is a clue. There's a clue on the slide. So the number of particles, the number of atoms that we're talking about that's present in 12 grams of carbon-12 is that number that we're seeing right here. 6.02 times 10 to the 23. So any amount of a substance that contains that number of particles, we refer to it as the mole. So it's a unit. That number is called Avogadro's number, or the Avogadro's constant. Good to go. You can keep the chat going so we know that we're connecting. All right, so we know that we have chemistry. Cool. So the mole is really a unit of measurement, and it's normally represented by the variable n, which we call n number of moles. So you can get n equal 2 moles, n equal 0.1 moles, and so on and so forth. So you can think of it like a big dozen, but it's much bigger than a dozen, than 12. When we talk about the mole, we're talking about the Avogadro's number, and it's an everlastingly, unwieldingly big number. It's hard to follow, right? So it's the amount of substance that contains the Avogadro's number of particles of that substance. So as I said, think of it like a big dozen. And I hope you're not here to right now. We're discussing. This should be touching, connecting with what you already have been going through. If it's the first time, not a problem. All right. So the particles can be atoms. We're talking about elements like carbon. That's what gold. It can be molecules. We're talking about covalent compounds or diatomic elements like chlorine, oxygen, anything that ends in "ene" or "gen", those diatomic molecules. And it also can refer to formula units, like, one formula unit of sodium chloride, calcium carbonate, whatever it is. So these are the particles that we're referring to. They can be atoms, they can be molecules, they can be formula units. All right. So 1 mole of carbon atoms then would contain the Avogadro's number, which is 6.02 times 10 to the 23 carbon atoms. 1 mole of carbon dioxide molecule would contain the same Avogadro's number of carbon dioxide molecule. And if you're looking at formula unit, for example, sodium chloride, 1 mole of it would contain the Avogadro's number of formula units. And in that, you would have the Avogadro's number of Na plus ion, and you would have the Avogadro's number of Cl minus ions, just the same. So it's like a big dozen. All right. Now, that is how we look at number of particles, right? Now, the Avogadro's number can be used to determine the number of moles present in a substance. Just like how we know that 12 equal 1 dozen, we know that if we have that 12 doesn't look like 12, let's fix it. All right, so we know that if we have 12 eggs, that's a dozen eggs, right? If we're given, say, 6 eggs, we could figure out that what that is. If 12 is equal to 1 dozen, then six eggs, we could say that is equal to X. Or without getting into finding X, we just look and we realize that, hey, 6 is half of 12. So this is the same as saying 0.5 dozen or half a dozen. The same, we can do the same thing when we're talking about number of particles. We can, based on the number of particles given, we can determine how many moles are present. But it can be a little daunting because the Avogadro's number is big. That's 6 with 23 zeros at the end, much too big a number to comprehend. All right. So if we look at it though, we can figure it out, or we can just punch it into the calculator. It's the same relationship here. So N, number of moles, would be equal to the given number of particles divided by the Avogadro's constant. And the Avogadro's constant is 6.02 times 10 to the 23. So this is all theory. We're not going to spend much time on it. We can even leave this question: how many Fe atoms are in 30 grams of iron filings? If we have iron filings, how many Fe atoms will be present in 30 grams? This question is a little bit early. We're still looking at number of particles. Perhaps we could look at, yeah, it's a little early, but I think it's something we could try. How many Fe atoms are in 30 grams of iron filings? This is pretty much introducing the next concept, which is that of molar mass. So 1 mole of a substance contains Avogadro's number. And if you were to weigh out that, because we can't tell persons to go and pick up a set number, pick up Avogadro's number of atoms or molecules, you know, we need something tangible. So to get this intangible form around the macroscopic level, you would have to weigh this thing out. So 1 mole of any substance has what we call a molar mass. All right, so we're going to leave the calculation for now. So the molar mass can also be used to determine the number of moles present in a substance. So using this relationship, number of moles is equal to mass given divided by molar mass. All right, so in the case of the iron a while ago, the RAM of iron, we said, is 56. RAM of Fe is 56. So we were given 30 grams. All right, so that 30 grams, we can represent that as a fraction of the mass of iron, which would be 56 grams. So the molar RAM is 56, but the molar mass is 56 grams per mole. All right, so we could just set 30 grams divided by 56 grams per mole, and that would give us the number of moles. Anybody care to plug that in? 30 grams divided by 56, that would give us, that's a little bit over a half, that's 0.54 moles. All right, so that's the number of moles present. And then the question before asks the number of particles that would represent, or the number of atoms that's present in that. So if this is the number of moles, we could just take this and multiply by Avogadro's number. 1 mole contains Avogadro's number, so 0.5 mole. So in that case, 1 mole of Fe contains Avogadro's number of Fe atoms. So if we have 0.54 moles of Fe, then that would be equal to X. And to get X here, we would cross multiply, and we'd end up with Avogadro's number times 0.54, which would give us 3.25 times, okay, let's try that again, 6.02 times 10 raised to the 23, all of that times a half. So that will give us 3.01 times 10 to the 20 to the 23 number of atoms. So still a bit theoretical. So the number of moles present is 0.54, and the number of atoms, you said it's 3. The number of atoms would be a little bit over half, 3.01 times 10 to the 23. All right, still theoretical. Now we have another relationship or a concept that we need to appreciate. It's called the Avogadro's law, which states 1 mole of any gas under the same conditions of temperature and pressure, it contains the same number of particles. All right, and for this 1 mole of gas at RTP, there are 2 conditions. We're not looking at what the conditions are. Well, RTP, room temperature and pressure, and 25 degrees Celsius. And the volume there, the molar volume there is 24 dm³ per mole. And at STP, which is you know, 1 atmosphere and 0 degrees Celsius, the volume is a little bit smaller, 22.4 dm cube. That's the molar volume, and we'll use this in a little bit. So still on the theoretical side. So it follows then that, of course, there's a relationship between volume and the mole. 1 mole of a substance, if we're talking about a gas, 1 mole of that gas is called the molar volume. That molar volume would have a molar mass, and within that molar mass, you would have Avogadro's number of particles. So the relationship between volume and moles is given by what we would call a magic triangle here. All right, and it's not really magic after all. But anyway, so we take whatever volume we're given and divide it by the molar volume, and we get number of moles, just like with the dozen. Whatever number of eggs you're given, you take that and divide it by 12, and you would get your answer converted to dozen. Just like a week, whatever number of days we're talking about, you divide it by 7 and you convert it to weeks. Whatever number of, yeah, you get the point. We can convert days to year by dividing by 365 and a quarter, and so on and so forth. So that's that. Want to move away from the theoretical side. So there are so far 4 ways, you know, that we can use to represent number of substances. We can look at the mole, we can look at number of particles, we can look at mass, and we can look at we can represent amounts of substance in terms of volume. And we can move among all of these 4. We can go from moles to particles, from moles to mass, from moles to volume, and we can go from any of these to moles. All right, so we can convert among all 4 of them. All right, which leads me to this final slide before we actually start some work. So it means we can move from moles to volume. Liter is here, but 1 liter is the same as 1 dm cube, is the same as 1 dm cube. All right, so 1 mole of, you can move from moles to volume by multiplying by the molar volume. Depending on what it is, it can be, the conditions, it can be 22.4 dm cube or 24 dm cube. We can move from moles to number of particles by multiplying by the Avogadro's number. We can also move from moles to mass by multiplying by the molar mass. And of course, when you're moving from moles to anything, you multiply. But when you're converting to moles, we'll have to divide. There's a funny dance some students showed me the other day that they learn when they're moving from big things to little things, they multiply. But when they're moving from little things to big things, they divide. But anyway, we're not here to dance. All right, so that's pretty much that. And to make things a little clearer, I've kind of just simplified it. The mole is the big one, the one in the center, the central unit then. SI unit for moles of substances. If you move into volume, you multiply by the molar volume, VM, not Victoria Mutual. If you move into number of particles, we multiply by the Avogadro's number. If you move into mass, we multiply by the molar mass, which we can get from the periodic table if we're looking at elements. And we can get from the periodic table if we're looking at compounds, you know, by taking the different things that make up the compound. And, you know, if it's NaCl, we take 1 atom of sodium or 1 mole of sodium, 23, chlorine, 35.5, add them, we get 58.5, and so on. So that's pretty much that. There's more to it, but I'd like us to get into some practice. All right, before we do that though, things to bear in mind, 1 dm cube is the same as 1,000 cm cube. Again, the Avogadro's number is expressed as 6.02 times 10 to 23 particles per mole. The molar mass, the mass of 1 mole of a substance, is expressed in grams per mole. The molar volume, which is the volume that 1 mole of a gas occupies, is expressed in dm cube per mole. And molarity, which is telling you how many moles you have in 1 dm cube, it's expressed in moles per dm cube. If we're talking about mass concentration, then it's expressed in grams per dm cube. All right, G/dm cube. Just like how you see sugar, $100 per kg, you have to pay $100 for every 1 kilogram. So grams per dm cube, it's telling you what mass is present for every unit volume, which is cubic decimeters in this case. All right, so let's apply some of these principles to a few questions. All right, so the first one that we're going to be doing, and perhaps I should take a break here to send the questions, or I probably will send it a little later, and I'm just going to switch over so we can actually get to that. But better yet, I want to do this again. All right. And you might have seen this before. This one is June 2017. We're going to work 2A and B. All righty. All right, the place is a little quiet though. Are we still here?
Yes, sir.
All right, cool. So then let's hide back this and get back. All right, so Leslie was asked to weigh 0.2 moles of aspirin to be used in a supervised experiment during her chemistry lab class. Before doing so, she read the label at the back of the bottle shown in figure 4. I mean, it's like telling the parents to weigh out 0.2 moles of sodium chloride. They don't know what that is. You have to make it practical for them, give them terms they can follow. Aspirin drug, it's used as an analgesic to relieve minor aches and pains, fever reducer, and an anti-inflammatory inflammatory medication. Formula is there, C9H8O4. Molar mass, they've worked it for you, 180 grams per mole. Notice that the molar mass as a unit. So if they had said RMM, it would be dimensionless. RMM is 180, but the molar mass is 180 grams per mole. Melting point, boiling point, density. We're not so concerned about melting point, boiling point, or the density. Now, define each of the following terms, and whenever you see definition, that's just like 3 marks. The mole. What is the mole? 1 mark. For the definition, the mole. Someone that I mentioned it earlier on. Could someone just open the mic, state what that is? Hello? Right. Oh, persons are, okay, let's check. Okay, nothing from, okay, that was a while back. What's the mole? What would you write here? The amount of substance contained in 112, the amount of substance that contains Avogadro's number. All right, that could work. That could work. And I would piece the original, the first definition that was mentioned a little earlier, the amount of substance that contains as many particles as there are in 12 grams of carbon 12. You could write that, or you could be more direct. You could say it's the amount of substance, the amount of a substance. Where are we? Okay, come back. The amount of a substance that contains the Avogadro. You could just say the Avogadro's number of particles, or you could just state what it is, contains 6.02 times 10 to the 23 number of particles. You could also state it's the amount of substance that contains as many particles as there are in 12 grams of carbon 12 atoms, which is a definition by comparison. All right, molar mass for 1 mark. How do we state the molar mass? What's the definition? Chat, come on, put it there, light it up.
Mass in grams.
Mass of what? Mass in grams, so 1 mole of a substance. All right, you could say 1 mole of a substance expressed in grams. 1 mole of a substance expressed, 1 mole of a substance expressed in grams, and that would give us 2 marks. All right. Okay, let's try that again. Not getting that to come off. Already. Okay. Calculate the mass Leslie would have to weigh to obtain 0.2 moles of aspirin. 0.2 moles of aspirin, calculate the mass you would need to weigh. So we were told that the molar mass is 180 grams per mole. So if you wanted 0.2 moles, I mean, we can look at it and say 0.2 is what? 20%. 0.2 times 180, we can just look at it and figure it out. But we could also use a statement 180 grams is equal to 1 mole. So X grams is equal to 0.2 moles. And of course, we would cross multiply. That's just a line I'm drawing, you know, so I have more space to write. Cross multiply will end up with X being equal to 0.2 times 180. And when we do that, we'll end up with 36 grams. All right, or we could say number of moles is equal to given mass, which is in grams, over molar mass, which is in grams per mole. So if we want, how does that work now? We're looking at, we want to find mass. So if we want to find mass, we'd have to cross multiply in this case. So it would be to find mass, we'd have to multiply. So mass there would be equal to number of moles times molar mass, which is equal to 0.2 moles times 180 grams per mole, again, which gives us 36. So it does 36 grams. Jared, another student in Leslie's class, weighed 18 grams of aspirin. Calculate the number of moles. So it's they're checking if you know to convert from moles to mass and from mass to moles, but without even checking, if 0.2 is 36, and we see that this person weighed out 18 grams. 18 is half of 36, right? So if 0.2 moles is 36, then half of 36 would be 0.1 moles. But that is it, 0.1. You can just look, but you still show them the working out. Don't just write 0.1. Show them you're working out. So you would say number of moles is equal to 18 grams divided by 180 grams per mole, which is equal to 0.1 mole. That's 1/10. All right, good to go. So that's that. That's how we treat that. All right, so part B, ethanoic acid is one of the products of the hydrolysis of aspirin as shown in figure 5. All right, and you don't need, it doesn't matter, you don't need to have seen aspirin before. You just need to look at the equation that's given. You always know more than enough to actually do very well. You just don't want to be overwhelmed. You see something that doesn't look like something you always practice. It doesn't matter. You're like, oh, I'm seeing rings, aspirin, but that's not on the syllabus. The concept is there though. You've done equations, you know mole ratio, so you just use what you know to just work with what you know, and you will be fine. So they want us to calculate the mass of ethanoic acid formed when Jared's 18 grams of aspirin is hydrolyzed. All right, we can look at this in about 2 or 3 ways. All right, we'll probably look at both of them and you say which one you're comfortable with. So this is aspirin. We got the molar mass already, which we know it's 180 grams. So before we even look at that, this is saying 1 mole of aspirin plus 1 mole of water gives 1 mole of whatever that is. You don't even need to know what it is, right? And 1 mole of ethanoic acid. And 1 is in front all of those, but just like in math, when the coefficient is 1, we don't say 1x, we just say x. So it's a 1 to 1 to 1 to 1 mole ratio. So if we know oh my, they've given us so much right here. They've given us even the molar mass of ethanoic acid. We don't have to work it. 12 plus 3, 15 plus 12 plus 32 plus 1, 60. So everything is there. It's set out for us. So This is 60 grams. So from this, we can write our statement. We know that Jared used 18 grams. So we could just write out 180 grams of aspirin produce 60 grams of ethanoic acid. Right? So Jared's 18 grams of aspirin, 18 grams of aspirin that Jared used would give us X grams. And then just by looking at it again, you see the relationship between 18 and 180. They don't want to trick you on the examiner. They're just using simple questions, simple concepts to check if you understand. 18 is 1/10. 54, I don't get the 54. Look at the relationship. 18 is 1/10 of 180. So, you know, it's ratio and proportion. 180 is to 60 as 18 is to X. We could divide both, we could, you know, take your time with it. So there's a relationship between the 18 and the 180, and they deliberately, that is it, I'm seeing it, I'm seeing the answer. They deliberately use numbers that divide, that go into each other nicely. Like 18 is 1/10 of 180. You know, but we could just go the root and say, that's all right, man, that's all right. It's a learning process. So we could just go the root and cross multiply. Let's change the color so we can see what's happening. So we'd end up with 180 grams times X is equal to 18 grams times 60 grams. Divide both sides by 180 grams to make X the subject. We never had to do all of that. And we're seeing what's happening here. 180 cuts 180, and then we have 18 over 180, which is 1/10. 18 into itself, 18 into 180 goes 10, how many times? 10 times. So we're left with 60 grams divided by 10. 60 grams over 10, which will give us 6 grams. So we look at it, 18 is 1/10 of 180. So whatever X is equal to, it's going to be 1/10 of 60, which is 10. So we can leave it there without even converting to moles. We can just write the relationship between aspirin and ethanoic acid, a standard statement connecting those two. Then we put in Jared's 18 grams under 180 grams for aspirin. We're keeping apples together. In this case, aspirin on the same side as aspirin, ethanoic acid on the other side. And then we find our unknown. So we'd end up with 6. All right. That's part B. That's part B. So we continue. We're going all the way to here, all the way in part B. All right. So that's that. So we'll move on to the next one. And this is a recording, so we can always go back. All right. In the next part now, we get to balance equations. All right, still still mole concept at play. All right, so write a balance equation for the reaction between calcium carbonate, acid bases, and salts, but you know, still related to moles. Balance equation for the reaction between calcium carbonate, nitric acid, and a carbonate. What do we get? Put it in the chat or open your mic. It's okay to give a chorus. Acid plus carbonate, what will we get? When an acid reacts with a carbonate, we'll get, okay, let's see what's coming in. We'll get salt, carbon dioxide, water. All right, very good. Salt, water, carbon dioxide. So let's punch that in. So that's calcium carbonate, CaCO3, put our state symbols, that's a solid, plus HNO3, nitric acid, aqueous. Aqueous acids are good electrolytes. You know, the strong acids are strong electrolytes as well. That's a dot. So this will give us calcium nitrate, Ca bracket, NO3 bracket 2. All nitrates are soluble. So we put that as aqueous, CO2 gas plus H2O liquid. And of course, we have 2 nitrate on the right. So we need to put a 2 in front of the HNO3. So everything else is in check now. 2 hydrogen on the left, 2 hydrogen on the right. So we're balanced. All right, this part now, part 5. So 2 marks like that. Part 5 is asking us, calculate the volume of gas that can be obtained from reacting 1.8 grams of calcium carbonate with dilute nitric acid. And they've given us the RAM of carbon, oxygen, and calcium, and so on and so forth. So I don't necessarily like to do a lot of conversion, but some persons, based on the book they use or the approach they're encouraged to convert whatever they're given to the moles to mole, and then convert from mole to the desired unit. You can do that, it works as well. 1 mole of gas occupies 24,000 cm cube at RTP, which is the same as 24 dm cube. All right, so they want us to find out the volume of gas. So we're concerned, this is a different color. We're concerned about volume of gas and mass of calcium carbonate. All right, so from this equation, 1 mole of calcium carbonate reacts with 2 moles of acid to give us 1 mole of carbon dioxide. All right, so we could work with the mass straight up and just see what happens, or we could convert the mass of the calcium carbonate here to moles, and then, you know, we take it from there. So which approach would you like to do? It's not about me. I want to know what you're working with. Which approach would you like us to do? You want us to work in with the masses straight up? Put it in the chat or answer. Which one would you like us to do? Let me check. Work with the mass. Somebody says masses, please work with the grams. All right, so we can do both. All right, so straight up. So we'll have to calculate the molar mass. So we have the RAM. So this calcium, CaCO3. Come on. There we go. All right, or not. Okay, CaCO3. Let's put that in. So we have 1 calcium. So that's 40 plus 12 plus 3 times 16, 48. 8 plus 2, 10. 4 plus 1, 5. Yeah, I like this because this gives 100. 5 and 4, 9 plus 1, 10. I like this one. So calcium carbonate, that one gives 100. So the molar mass of calcium carbonate, so molar mass of CaCO3 equal 100 grams, 100 grams per mole. So from this equation, whereas we can write a standard statement of fact connecting the 1 mole of calcium carbonate, which has a mass of 100 grams. So we say 100 grams of CaCO3 react to give, and we could just work directly. So we know that it gives 1 mole, let's highlight, it gives 1 mole of what's that? 1 mole of CO2. But we also know that 1 mole of CO2 has a volume, occupies a volume of 24 dm cube. So we can just write that up, you know, directly. So 100 grams of the calcium carbonate, then it produces 24,000 cm cube of CO2. So we're saying then, what if we used 1.8 grams of CaCO3? Would you be expecting more gas than what's produced when we use 100, or would you be expecting less? 1.8 versus 100, we'll be getting more or less. Check to see what I was saying. We'll be getting, okay, no answer yet. 100 grams gives 24,000 cm cube. We're using far less than 100 grams. So are we expecting more or less? All right, we're expecting less. So we put X over here now, and we solve. Of course, X is going to be equal to, what's X equal to? So let's see, 100 grams times X is equal to 1.8 grams times 24,000 cm cube. Divide both sides by 100 grams to make X the subject. So there we have 1.8 grams as a fraction of 100 times 24,000 cm cube. So that's 1.8 divided by 100. So that's 0.018. 1.8 divided by 1.8 divided by 100 times 24,000 cm cube. And we end up with X being equal to 432 cm cube. All right. So the less conversion you have to do, yeah, well, well, I don't want to say it's a personal thing. Since you asked for mass, we worked directly with mass. But I'm going to use a different color now to look at a different approach. We could have converted the 1.8 grams. So we could have said moles. We could have said number of moles of CaCO3 is equal to 1.8 grams divided by 100 grams, which would give us 0.018 moles. And because it's a 1-to-1 mole ratio, we could now say that, hey, since it's a 1-to-1 mole ratio, we could say 0.018 moles of CaCO3 produce 0.018 moles of CO2. And then we want to convert that number of moles to volume. So we could say, hey, the molar volume at RTP is 24,000 cm cube. So if 1 mole gives us 24,000 cm cube, then we could just say 24,000 cm cube, times 0.018 moles will still give us 432 cm cube. All right. So I put both of them there. So those who are in favor of the other one, you're not left out. All right. So let's another one. So we'll have to use here, or we'll have to stop this one. Go again, and it should be good. All right. So that was the first part. We know at June 2014, question 2. All right. So this one. All right. Calcium nitrate decomposes under strong heat according to the following equation. And the equation is there. This comes up a lot. Well, let me not say where it comes up, since we're not supposed to have those questions. So this is a good equation to know. This is a good equation to know, especially for your multiple choice. All right. So that looks like it would be a good multiple choice question. All right. So check this out. This time the mole ratio is different. The mole ratio is not always 1-to-1. We tend to do a lot of questions with 1-to-1 mole ratio. And then when we get other ones, no, we're stuck. All right. So the mole ratio here of calcium nitrate. Well, before we even go any further, let's answer the question at hand. What visible change would be observed when calcium nitrate decomposes? Well, oxygen is a colorless gas, so we're not going to see anything for oxygen. We could test for it using a light, using a, what do you call it, a glowing splint, and it makes it glow brighter or more brightly, or even relights it. But they're not asking us about, well, we can't see that. What we could observe when this happens is we would observe, let's just get to the point. We would observe brown fumes. That's how we identify nitrogen gas. Brown fumes. And it's acidic. So if you use blue litmus, it would turn it to red. All right. People tend to confuse brown fumes from NO2 or nitrogen dioxide's brown fumes with bromine gas, when bromine is in the, the vapor form. Don't mix them up. Don't mix them up. All right. Context. So brown fumes. They're saying here 5 grams of calcium nitrate are decomposed completely. Calculate the volume of nitrogen dioxide produced at RTP. 1 mole of a gas again occupies 24,000 cm cube at RTP, and they've given the RMM of calcium. They should say RFM. They should say RFM because this is ionic. But anyway, they said RMM for this is 164. All right, so we'll have to look back at our equation. We're concerned about calcium nitrate, and we're concerned about volume of gas. All right, we can do the same approach. We can do the mass approach, or we can do the moles approach. All right. So since we started with mass a while ago, let's start with moles this time. From this equation, we're seeing where 2 moles of CaNO, well, calcium nitrate, the mole ratio of calcium nitrate to nitrogen dioxide is 2 to 4 or 1 to 2. When you simplify it, you get 1 to 2. So what I would do, what we can do in a case like this, to find the volume of gas that's going to be produced, we could convert the 5 grams of calcium nitrate that's given to moles. So we could say 5 grams of Ca, or better yet. All right, let's make it as systematic as we can. So we could say moles of Ca, of calcium nitrate, is equal to 5 grams divided by 164 grams per mole. When we get that, 5 divided by 164, that will give us, that's equal to 0.03 moles. All right. So we know we take that and we say the mole ratio between calcium nitrate and what's that? Calcium nitrate and nitrogen dioxide is 2 to 4 or 1 to 2. So the number of moles, or better yet, we'll say, since it's a 1 to 2 mole ratio, we could state that when 0.03 moles of Ca of calcium nitrate react, when 0.0 moles of calcium nitrate react, twice that number of moles of nitrogen dioxide is formed. 0.03 times 2 moles of NO2 are formed. 0.03 times 2 is 0.06. All right, so which is equal to 0.06 moles. We could now convert that 0.06 moles to volume. So we could convert 0.06 moles of the nitrogen dioxide to volume. So we could say 1 mole of NO2 occupies 24,000 cm3. So if I have 0.06 moles of NO2, it's equal to X. And we solve for X and we'll end up with that 0.03 times 2, 0.06 times 24,000. And we'll end up with X being equal to 1440 cm3. Depending on which approach you take, or when you round off or when you round up, you might get 1463, 14 something, but as long as you get 1400 and something, you're good to go. All right. So this is the moles approach. We could have worked directly with using mass. And for this, I'll just use a different color. Same thing, but some persons are more comfortable this way. So we know the molar mass of calcium nitrate, it's 164 from the balance equation. 2 times 164 grams of the calcium nitrate. Following the equation, it gives us 4 times whatever the mass, sorry, not the mass, 4 times 24,000 cm3 of NO2. That's what 4 moles mean. 4 moles of NO2 are formed, so it's 4 times the molar volume. So we want to find out if we had 5 grams of Ca of calcium nitrate, what volume would we get? And it's the same principle. We're cross multiplying, so it would be 2 times 164. That's 328, so it would be 328 grams times X, which is equal to, that would be equal to 5 times 4 times, what's all of that? 5 times 4 times 24,000. Just keeping it there so we can see where all of that is coming from. Divide both sides by 328 grams. Yeah, some grams in there too. So 5 grams times 4 times 24,000 cm3. Divide both sides by 328 grams. And we'd be left, I mean, when we're going to do it like this, 4 times 24,000 is 96,000. 96,000 times 5. Then all of that divided by 328, and that would give us 1463 cm cube. And in this case, the difference is it's fine. We would have converted to moles here, and we rounded, you know, we took it to 2 decimal places. But what's important, the difference here is in 1, 2, it's the third significant figure, you'd still get the marks, all right? So some persons would convert to moles, then they do the computation. Some persons would just stay and just write the relationship between mass of calcium nitrate and volume of the gas and just work directly. Either way either of them works, all right? I just want to ensure that I didn't lose anyone. All right, 1440, all right, somebody got 1440. Similar to what's there. 720, if you got 720, you did not take into account the mole ratio. Remember, it's 2 to 4 or 1 to 2. All right, so 1720 looks like half of 1440. So, oh, you picked it up, you saw it, it's the same person. All right, good to go. So then, those are when we're talking about dry, you know, dry amounts, dry masses, dry amounts reacting. And let's see, all right. Oh, that is that. All right, 59. So we have another mole question, but looking at the time, I want us to touch on salt prep. I want us to touch on salt prep. I won't say coincidentally, I have this, you can check this out on the channel. I've worked this already. You can check it out, January 2018. Well, the whole paper as a matter of fact. But if we go through this, we're going to finish and we would have only covered one part. So going to slip back to acid basis salts. Want us to look at that, but the best way to look at salt prep is to really work on salt prep. So I'm gonna just fast forward somewhat to salt prep. Question on salt prep. All right. All right, so we'll use this one going into it. This one is on this one is a little different, so it will build up to this one. We'll go a little faster. 1, 2, 3. Let's share again. Where are we? All right, there we go. Phosphoric acid H3PO4 is, where are we? It's a common additive in most soft drinks. It can react with hydroxide and alkali to form both normal and acid salt. Define the term acid and alkali. What's an acid? You know, for 1 mark, you can use 3 words to define that. What's an acid? Type it, 3 words. Can you define an acid in 3 words?
A substance that neutralizes a base.
All right, substance that neutralizes the base. Little third, a proton donor, a little third form there. It neutralizes a base, but for, you know, at this level, they want you to focus on the fact that, you know, they want you to focus on, you know, the fact that acids dissociate to produce H+ ions. So yes, we know that's what you just did. It's more like a property of acids. So yes, it will neutralize a base. So a substance that neutralizes a base is an acid. So it's correct, but can I say the more correct answer? A proton donor.
To form salt and water?
You would get the mark. You would get the mark. You would get the mark. We're also looking for a proton donor or a substance that dissociates in water to liberate H+ ions. All right. Is it okay for us to just say the answers instead of writing? I'm just looking at the time. I want us to touch on all 3. You'd have to respond though, because you know it's up to you. Where are we? Not seeing any responses. Yes, sir. All right, good. So all right, so acid here is all right, yes, sir. 1 person responded. All right. So we could say it's a proton donor, meaning it's something that will give up a proton. And an alkali is a base that's soluble in water, a base that dissociates to give. So it's a base or a substance that dissociates. You could say a substance as well. And when you're not sure, you can always say a substance. It's safe to say substance. A substance that dissociates in water to give OH minus ions. All right. Define the term acid salts. All right. So acid salt would be substance formed when, so it's a substance formed. Note, substance formed when only some of the H plus ions in an acid are replaced. And of course, the replacing here, the replacement is taking place. It's been done by the metal ion or the ammonium ion. So those where you have only some of the H plus ions are replaced, you call it an acid salt, because in truth and in fact, yeah, H plus are replaced, so it's an acid. But if H plus are still there, sorry, H plus are replaced, you'd get the salt, you know, nature of the salt there, properties of the salt. But if H plus are still there, it's going to still have acid properties. So we call it an acid salt. And then the normal salt now would be the substance formed when all the H plus ions are replaced. So all the H plus ions in the acid, substance formed when all the H plus ions in the acid are replaced by the metal or the ammonium ions. State the molecular formula for the normal salt formed from the reaction between phosphoric acid and sodium hydroxide. So H3PO4 it is. So if we're going to have the normal salt replace all of the H plus with sodium, we'd have to replace all three of them. So it would be Na3PO4. Yes, PO4 is 3 minus. So we have all of 3H plus going with that. So if we're going to replace, we're going to replace with 3Na as well. Balance equation to show the formation of the normal salt. So we'll use H2SO4. No, that's sulfuric acid. We need phosphoric, T9. So it's H3PO4. And we use NaOH, and we always, so the salt comes next. It's normal Na3PO4, salt and water. It's neutralization plus H2O. So we work with what's in the salt first, Na3. So we'd need a 3 here. Okay, putting a 3 there gives us a total of 6 hydrogens. 3 there plus 3 here. So that's 6. So we put a 3 there, and that sorts that out. Right. So that's that. Then let's see what they want. They want next the molecular formula of an acid salt formed from the reaction. We have options. Okay, since we're talking acid, I like to do it in red. All right. Because acids turn blue, it must turn red, H3PO4. So we have option. We can replace, we saw where for normal, we saw where we have Na3PO4. So if we're replacing some, we can replace 1. So we can have Na2HPO4. We can replace 2. We'd have Na, and we only. So we replace 2 in the top one, and in the bottom one, we're replacing only 1 of the hydrogen. So we have options. So it's either Na2HPO4, sodium hydrogen phosphate, or, so we'll call this 1, or 2, NaH2PO4. Balance equation. So we're going to use 2 equations depending on which one you're using. So if you use 1 above, we would use H3PO4 aqueous, same sodium hydroxide, aqueous, and we'd end up with, let's write our acid salt, Na2HPO4 aqueous plus water. No, we can't say this one. We have to write this because it's equation. It's another language. So we have to write this one. All right. So we balance. We start with the salt. We have Na2, so we need 2 Then we look at our what we need now to balance off. So we have a total of 3 hydrogens here. Going to have to take that off. So we have 3 hydrogens here, and we have 2 there. That makes 5. So we would need that 3 plus 2, 5. We have 1 here. So 2 there, yeah. 2 plus 3, 5. All right, so what do we need to do on the right side to balance this? Chat, check in the chat. All right, let me see. One response. Yes, sir. No answer. So we need 5. We have one on the right side already. So what we would do, we would just need to put 2 right here, 2 in front of the water. Very good. We'll have to give it time for the communication to take place. All right. So we can put a 2 right there, and there we have it. 2 2s 4, and we have 1 already, making 5. If we use option, the other one, because no 2 persons necessarily think the same way, we would go again H3PO4 plus NaOH, and the salt we're using now is Na, a sodium dihydrogen phosphate plus water, outer space. All right, so let's balance now with blue. So we have 1 sodium, so that, let's look if everything is intact. Let's see, we have 4 hydrogens, 1 from the sodium hydroxide, 3 from the acid. Over here we have 2 from the acid salt and 2 from the water, so that one is balanced, just as it is. Solution of 0.05 molar phosphoric acid has a pH of 4, solution of 0.05 molar sulfuric acid has a pH of 1. Which of the 2 acids is stronger? We're using pH now. Which of the 2 acids will be stronger? Sulfuric, and that is the one with the lower pH. So it's H2SO4. Jeffrey complains of pains due to excess stomach acid after consuming too much orange juice. That's a lot of orange juice. 2 acids present in orange juice. Open the mic. Finish strong. It's orange juice, so we'll have citric acid because it's a citrus. So citric acid, and if you do bio or family and consumer management, you know that something else is in acids that prevents scurvy. What do we call it?
Vitamin C.
Vitamin C, and then the name vitamin C, you can call it, well, let's say, I almost wrote AKA, ascorbic, ASCORBIC, ascorbic acid. All right. And then, of course, if you have acid stomach, similar to the answer that someone gave earlier, if we have acid stomach, the type of chemical reaction that takes place in the treatment of excess stomach acid. I want to move this, but the writing is not moving. So let's get this going again. All right, so excess stomach acid, the name for that is definitely neutralization. Excess acid, we need to mop it up, so we need a base. So this would be a neutralization, neutralization. Hence, name one substance that can be used to treat excess stomach acid. The problem that we have here, persons tend to give brands, like name brands of substances, but we don't want a name brand. So, you know, you could not say Andrew's salt, even though we use it for acid stomach. You couldn't say Andrew's salt. Here, you have to state what is in Andrew's salt that you're using. What's the active ingredient in Andrew's salt that you're using? So what could we use? There are 2 things we could use here. And you can't give the brand.
Baking soda.
Baking soda. Well, that tastes awful. You know, it could work. It could work. What's the scientific name for baking soda?
Hydrogen carbonate.
Hydrogen carbonate. Or did you not
Sodium
open them?
bicarbonate.
Sodium bicarbonate. So we could use baking soda. Where's my right? So we could use baking soda. Tastes bad, but it could work. Well, most of them taste bad anyway. So we could use baking soda. That's NaHCO3. We could use magnesium hydroxide. We could use magnesium hydroxide. In fact, that is used to make one of them, we call it milk of magnesia, but that's a brand. And Tom's Deca, but no, you don't put those answers because those are brands. You have to give the active ingredient that's present. All right, good to go. So that's that. And this is not coming off. All right, so that's another one. That's how you call it now. That's the solve question. Let's go again. I think I probably was ambitious by having two solves question, but that's fine. Whatever we miss here, can always do something. If we miss the electrolysis, you can always do something to get that. Calcium carbonate and sodium nitrate are two salts that are used in the manufacturing industry. Define the term salt. Define the term salt. What's a salt? So earlier we had mentioned a salt is a substance. Well, we didn't define salt, but a salt is a substance salt is,
oh, sorry.
yeah man, go ahead. Substance form, go ahead.
When hydrogen ion is replaced by metal?
Yeah man, substance form when H plus ions, when some or all of the H plus ions, or when H plus ions are fully or partially replaced by the ammonium ion, that NH4 plus, or metal ion. All right, and they're asking us to identify one product that each of the salts mentioned above is used to manufacture. So what can we use calcium carbonate to make? Everybody in Jamaica, a lot of construction is taking place now. Hello? Go ahead. Go ahead. Still listening. Checking the chat as well. Limestone. Not sure about the steel. Not sure about the steel part. Not the steel. It's the other part. No, don't let them get you. So calcium carbonate is found in limestone. So we use it to make we use it to make cement, calcium oxide, which gives us cement. Cement, as my little boy will call it. All right, so what about the other one? What do we use it to? What do we use sodium nitrate to make? So cement, for the calcium carbonate, we use calcium carbonate in the manufacturing of cement. What do we use sodium nitrate to manufacture? Sodium nitrate, think about it. We use it to manufacture where? What's happening in the chat? All right, so in the interest of time, we use NaNO3 sodium nitrate. It can be used to manufacture fertilizers and also explosives. All right, so we can work with that. All right, just so we get this off and we go. Outline the laboratory preparation of a pure dry sample of calcium carbonate. Include in your response a balanced chemical equation. So whenever you're gonna make a salt, the first question to ask ourselves is what?
Is it soluble?
Is it soluble? If it's insoluble, we're going to use ionic precipitation. Ionic precipitation. All right, so in this case, we would need two soluble salts, each containing the ion that you're making. Sorry, each containing ions of the salt that you're making. So if we're making calcium carbonate, we're going to need something that contains calcium, a soluble salt that contains calcium. And we need a soluble salt that contains carbonate. So we could use calcium nitrate since all nitrates are soluble. Calcium nitrate, all nitrates are soluble. So let's get to the equation. All nitrates soluble. We could use sodium carbonate, seeing that the salt of sodium, ammonium, and potassium are also all soluble. So this would give us Ca, this would precipitate out to give us calcium carbonate, and we would end up with NaNO3 aqueous, but two of it. So it's not, you can use 420 mils of CaNO3 solution into 20 mils of Na2CO3 solution and stir. So that's step one. Step two, filter mixture and retain the residue. The residue is the calcium carbonate. 3, pat dry the residue. Pat dry the residue in filter paper. Oh, line. So we don't just filter, retain. Before we pat dry, let's cross out this one. We need to rinse residue in small amount of distilled water, small amount of distilled water. Then 4, you pat dry the residue in filter paper or paper towel, and we're good to go. All right, that will do it. All right, so the next one, the other part, and it seems we'll wrap with this one. We'll make a promise for the other part. Write a balanced chemical equation with state symbols to illustrate how sodium nitrate can be prepared in the lab. So we said when we're making a salt, we ask if it's soluble. So this one is a soluble salt. If it's soluble, we need to go a little further. We need to go a little further and ask, what's the other questions that we ask? If it's soluble, we're going to go a little further. We couldn't use the same method. We couldn't use ionic precipitation for sodium nitrate, right? Because I mean, all sodium salts are soluble. So there are no insoluble salts of sodium. So we could start there. There are no insoluble salts of sodium. Salts of sodium, potassium, ammonium are soluble. So there's no insoluble salt of sodium. So ionic precipitation could not work. All right. So did they ask us to write a balance equation to illustrate? So balance equation illustrating how we would have to use an acid and an alkali. We can't use acid and the sodium in this case, acid and reactive metal. What's happening here? Right, so the equation we're going to use HNO3, so nitric acid and sodium hydroxide. The sodium would have to be supplied by an alkali here that's solubly, well, redundant because alkali is soluble in water, base soluble in water. So we couldn't use acid and the reactor would be exclusive. This will give us our sodium nitrate, NaNO3, and water. And we said that the method uses that to with symbol to illustrate that. So that's what we'd use. So you get about 3 marks, 2 marks for this. Then we also would state that the reason for this one is the equation that will tell us the technique. And then the reason we're not using ionic precipitation will state ionic precipitation not suitable because sodium has no insoluble salt. And to put icing on the cake, you could say all, well, that should be common A. All salts of Na K and NH4 plus are soluble. All right. So they said that to illustrate. So we'd use, in this case, we're using we would use titration. All right, titration using acid that was mentioned just now, HNO3, and alkali NaOH. All right, so that's that. All right, so that's that. Any questions? So we've come to, this is we have another one. This is do. I think I was probably ambitious. I was ambitious with six questions. But just before we go, I'd like us to touch on a little electrolysis. So gonna just scroll down to that one. All right, to just stop it off, so at least we'll have some form of, closure, completion. We'll focus on some electrolysis and post it, so you can check that out. You can check that out a little later on. All right, on the channel, that is Chem with Chem. All right, so this figure 3 shows a simplified diagram of the apparatus used for the electrolysis of aqueous copper 2 sulfate using platinum electrodes. All right, so key. Yeah, same here. It's a little blurry for me as well. Probably it's the bandwidth now. All right, perhaps I should close my camera. Probably that would help. All right, is it better now? It's still a little blurry. All right, I'm seeing it. So keyword here. All right, deduce the oxidation state of sulfur here. How many marks they're giving us for this? All right, the sulfur here. Let me check this out. CuSO4. CuSO4. So oxidation state of copper here is +2. We don't know sulfur. Plus 4 times -2. All of that is equal to 0. So this is +2 plus x minus 8 equals 0. X, what's that? -6 equals 0. X equal +6. So this is a +6. At the anode, the hydroxide ions are discharged in preference to the sulfate ions. It's copper 2 sulfate, so ions present would be Cu2 plus aqueous ions, SO4 2 minus aqueous ions, H plus ions, and OH minus ions. So they're saying the anode, the hydroxide ions are discharged in preference to the sulfate ions. State the reason for this. The OH minus ions are lower in the electrochemical series. I'm writing ECS. Electrochemical series, no shortcut. So it's lower in the series, so it will be liberated preferentially. The hydroxide ions, so we did that already. So that's the reason it's lower in the series. In the electrochemical series, it requires less energy to be discharged. Balance equation for the reaction of the anode. So this is one of the few things I ask students to commit to memory when OH minus ions are liberated. It's 4 OH minus ions to give 2 water, oxygen, which will bubble, effervescence, and 4 moles of electrons. From the equation written in C above, state whether the reaction at the anode is oxidation and reduction. Give a reason. Now, without even knowing the reason, it's at the anode, so you could say oxidation. Oxidation always occurs at the anode, but you look to see what's happening. Electrons are lost. See, we end up with electrons at the end of the day. Electrons are liberated. So you could say loss of electrons. All right. Or we could use, what are we going to use for this? We could use the oxidation, change in oxidation number. The oxygen here is -2. Hydrogen is +1. Here, the hydrogen is still +1. This oxygen is still -2. But over here, don't mix up the -2, what's in the bracket. What's in the bracket is L. Over here, the oxidation number of oxygen is 0. So we had an increase. You could say there's an increase in oxidation state of oxygen from -2 in OH minus to 0. Let's write out the word 0. 0 in O2. That's us over answering somewhat, but that's fine. State 2 changes that occur in the electrolyte. Now, to look at what's happening in the electrolyte, or to understand what's happening in the electrolyte, we'd have to look at what would be liberated. And for this, we deliberately want blue. So the Cu2 plus is responsible for the blue appearance of the solution. They didn't ask us what's happening at the cathode, but we know that OH minus has been liberated. So it means that OH should be removed from the solution. If it's a competition between copper and H plus, copper is below hydrogen in the reactivity series. So copper would be liberated preferentially. So you're pretty much, in essence, we're removing copper from the solution. So copper gives the solution its characteristic blue. So the solution would become paler. So it would become decolored. So it would move from blue to pale blue or to colorless eventually. So find a way to say that and then check this out now. If that's happening, so we'd say solution decolorizes, solution becomes pale, or the blue color disappears. Anything you want to say becomes pale or less blue, whatever. And then if we're removing copper and OH minus, all we're left with now is H plus and sulfate. So the H plus and the sulfate would combine, and then that would form sulfuric acid. So the solution is becoming acidic due to the sulfuric acid. The H plus would combine with the sulfate to give H2SO4. You don't put that in the answer, just put it there for you to see. Determine the mass of copper in grams, which will be deposited at the cathode when 5 amperes of current passes through the electrolytic cell for half an hour. We would need the cathode reaction for this. Cu2 plus gaining 2 electrons to give Cu solid. All right, so from this, we're seeing where 2 times 96,500 coulombs, right? Also known as 1 Faraday. So that the passage of that amount of current has to take place, has to happen for us to get 64 grams of copper, because as we can see, 1 mole of copper is produced here, but we don't put the 1, so we can put the 1 right there. So 2 times 96,500 coulombs produce 64 grams of copper. Now, if we use 5 amperes and we pass that for how long? Half an hour. We're going to have to convert that to quantity of electricity. So we're going to say Q equals IT. Current strength in amperes, that's 5 amperes times time in seconds. So that would be 30 minutes times 60. So that's 5 amperes times, what's that? 6 3 is 18, that's 1800 seconds. Ampere seconds the same as coulombs. So we do that, 5, 10, 5, that's what, 9,000? 9,000. Yep, so that would be 9,000 coulombs. So let's rewrite this statement. Let's use blue. 193,000 coulombs liberate 64 grams of copper. Suppose we had 9,000 coulombs. Would expect less. So X here would be X times 193,000 equal 9,000 times 64. Divide both sides by 193,000. So we see that that's 9,000 divided by 193,123. That's 0.047 times 64, which would give us 2.98 grams. And that's it for 4 marks. And then to top it off, they're saying, hey, how indicate how the apparatus in figure 3 can be modified to obtain pure copper from impure copper. If no modification is required, right? No modification required in the relevant space. So need to look back at the diagram, flip over the page. We don't have a page. So if you want to do what is it, what they call it, the purification of copper from impure copper. So okay, we'll just do it on the diagram and we know what we'll put in the space. So if we're going to purify impure copper, we know that this is the anode over here. So that's the anode. So we need to replace anode with impure copper. And then for the cathode now, at the cathode we need to place a piece of pure copper. So place a piece of pure copper as the cathode, not as the cathode. You really want the copper to be collected on a piece of pure copper, so you don't have to be scraping off copper off platinum, which means you would have impurities again. And then whatever, so this you replace this with a piece of impure copper. So the impure copper goes here, and whatever impurities in it would fall out to the bottom of the container. All right, the solution for the electrolyte, no modification. I don't remember if they asked us for that. For the electrolyte, let's see. Yes. So yeah, anode, replace anode. So here we are. So replace, so this is for the anode. Replace the anode with impure copper. Place a piece of pure copper at the cathode, and for the electrolyte, no modification. Okay, let's fix that. All right, so this is what we want. Get rid of that, get rid of that. So no modification for the electrolyte. So for the electrolyte, no modification. For the cathode, we're replacing a piece of pure copper at the cathode, and for the anode, replace it with the impure copper. All right, so that's basically it. I think probably was a little ambitious, but we touched on all 3. As we mentioned at the beginning, it's not meant to cover or solve all the problems. It's really meant to stimulate you, make things a little clearer. And I definitely am committing to working some more electrolysis questions. I don't think we have enough electrolysis questions out there. So this one just now was, you can write it down, you've got this on the bed. That was May, June 2012. So you don't have many electrolysis questions. All right, you didn't have electrolysis for like 3 years or so. So I'm going to do a medley so we can get more practice. You can compare your answer with my answers and so on and so forth. So this is it. We've come to the end of today's session. School is over for today. We have finished our work, finished our play. All right, Miss Hilton, back over to you.
Thank you, sir.
Thank you, sir. Guys, I want you to place, the link is in the chat for the evaluation of the workshops. I want to thank you all for coming, and I want to say a big thank you to our presenter, Mr. Camille Walford. And guys, I just want you to, before you go, use the reactions or type in the chat, how you feel about the workshop today, if it helped. And please remember to click on the link I can resend it, but you can click on the link. If you're not seeing the link, just let me know, so we resend it. Right, so just let us know how you feel about Mr. Walford and the presentation today and whether or not it helped. This will help us as well to make the presentations better and bigger for the future generation, right? So please leave your feedback. I want to say a big wow, thank you to Mr. Walford. Truly phenomenal presentation, and for taking the time out to be here today at quite short notice. But thank you so much, Mr. Walford. Words cannot express. Will we be using this space or the creating a breakout room? Sorry about that. Words cannot express just how grateful I am. So I just want to say a big thank you again. All right. Bye. Thank you. Give Mr. Walford a thumbs up or a clap now.